All right. Lost a little bit. Any questions?
Wow, everybody has like a chair between them the whole counting process, sitting in kind of different places.
You ruined. I had a pattern in my head. I was making a rule for why you sit where you sit. No, I don't have it.
It's about the same because there's two people at the beginning, and two people at the end.
Kind of, sort of. All right, countability. So the idea of countable is if the cardinality of a set is 0, 1, 2, 3, some sort of finite number. Not only is it finite, it's also finite and countable. But on the other hand, if the cardinality of the set is equal to the cardinality of the normal counting positive ints, 1, 2, 3, 4, which is aleph null, then S is called countable for either way. The nice thing about having this idea of forming that two sets have the same cardinality, if and only if there's a bijection from A to B. This also works for like large finite sets that you just don't want to count. So you have a lot of people show up and you want to find out if you have the same number of students as chairs. So you have a very large lecture hall, you just simply say sit down. And then you look. You don't actually have to count the students or chairs. You would say, oh look, there's no empty chairs and there's no standing students, they have the same cardinality. Well, what is our cardinality? Don't care. I have equal number of students and chairs. I actually can at least say that they have the same cardinality. And so that idea of forming a bijection, right, just go ahead and have a rule, students to chairs, please sit down, is enough to actually solve issues when we have the idea of things that are infinite. So let's look at these groups that are non-finite. That one day I had that Venn diagram, and here's all the sets that are finite. Well, what about everybody who's not? Could we form groups outside of that are of different types of the non-finites, different types of infinities? And the first one that we talked about would be based upon Hilbert's Grand Hotel, which would be the rational numbers. And for the rationals, if you look at the proof in the textbook, you can modify the proof in the textbook a little bit. We can write something larger than the rationals. And so we could consider the table, which this table includes Q. It's actually larger than Q, and we'll see why here in a bit. So what I'll do is I'll just have 0, and then I will have plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 4 over 1, plus or minus 5 over 1. I have no idea why I wrote a 6. Plus or minus 1 over 2, plus or minus 2 over 2, plus or minus 3 over 2, plus or minus 4 over 2, plus or minus 5 over 2, 1 over 3, 2 over 3, 3 over 3, 4 over 3, 5 over 3. Anybody getting bored yet? And finally, last row, plus or minus 2 over 5, plus or minus 1, plus or minus 4 over 5, 5 over 5. In this pattern, I would continue it. All right, consider this table for a second. And if we would look at it, there's a couple of features that I'm going to work on a bit for it. One is if we would consider the following diagonals. And if, go through here, let's do kind of a, let's do a light green, let's do a light yellow here. Is that light yellow showing up yet? And on those diagonals, I would call this a diagonal equal 1, diagonal equal 2, diagonal equal 3, diagonal equal 4, diagonal equal 5, diagonal equal 6. And so this would continue on. All of these diagonals are finite in length. The diagonals' length are 1, 1, 2, 3, 4, 5, and just notice how they just keep increasing by 1 as we go, right? So in the end, the diagonals are finite in length for infinity, right? Because I can count 1, 1, 2, 3, 4, 5. Every one of those numbers is finite. So all the diagonals themselves are finite. Things that I notice about the diagonals. About these D's. For any A over B, where A, B are ints, and B is not 0, I'm not going to say no common factors, right? Because there's ones here that have common factors. 2 over 2, 3 over 3, 4 over 4, 5 over 5, 2 over 4, 4 over 2. Those all have common factors, right? So these aren't fully the rationals, right? But they are at least, everything in this table is a int divided by an int, and the bottom is never 0. And the top is 0. I just used domination, and I just collapsed it to 0. Because 0 divided by anything is just simply 0, so that's just 0. But everything here, all of these are here, all are in this table. And not only that, A over B is in D equal A plus B. I know exactly which diagonal any of these are in. So if somebody said, well, you know, which diagonal would be 100 divided by 101? It would be on the 201st diagonal. And I know which diagonal any of these numbers will be. So everybody's here, and I know exactly which diagonal. What's important about that, it would be, if I'm going to start moving along the diagonals, I need to make sure that the diagonals don't miss anybody. You know, if you would sit there and say, well, how do you know that one of these diagonals just doesn't accidentally skip one rational number? And the answer is, well, it can't, because I can take any rational number, just simply add the top and the bottom, and that's the diagonal it's on. Nobody's going to miss anything by the closure. Why? Closure property of additions. You know, int plus int is int. That's it. So therefore, this diagonal will miss no one. So these diagonals are good in terms of counting. And so that will be our process of counting the rationals. So why is it the rationals are countable? Well, I need to form a bijection, right? To have countability, for Q to be countable, we need a bijection from Z plus to Q. So this first part is all the background information. I need to make the rational numbers. Well, this is actually bigger than the rationals. Not only is this larger than the rationals, how many times does the number 1 occur? An infinite number of times. How many times does a half occur? An infinite. How many times does every unique rational number occur? An infinite number of times. Not only is this the rationals, it's every possible way of ever writing a fraction that simplifies to the rational number. Now, if I want to just count the rationals, there's actually kind of two approaches to this. One approach would be to count the table and say, the table is countable. Well, how would I count the table? Well, I would count the table by doing this. I would say, okay, you go to room 1, the plus goes to room 2, the minus goes to room 3, the plus goes to room 4, the minus goes to room 5. We would do this whole go along and say, go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? I hit the positive number and the negative number. So I'm sending the positives to the even rooms, the negatives to the odd rooms. Now, these are, in their entirety, countable. And if a larger set is countable, the smaller set should be countable, but we would have to prove a thing like that. Okay? The other approach is to say, well, I could count the entire table and say since the big table is larger than the rationals and the big table is countable, the rationals must be countable. The other way is to just count the rationals. So what would you do is you walk along your diagonals. The moment you hit something that was not rational, what would you do? Skip it. You go along. Hey, you're not rational. Skip. And you go to the next one. Up. Let me see. That one's rational. Let me see. That one, that one, that one, that one, that one.
There's all those in that diagonal.
Yeah, all the main diagonal would be not.
There's like a whole bunch of slopes in there.
Yeah, really what they are is if you look at it, like if this one is, see the 1 and 2? Down 2 over 1 is always out. And like this one, this would be over 2 down 1 is always out. And so that not only does the rational tell you, it tells you which ones to get rid of.
What about 1 over 1 would still
Would always be the diagonal, right? Just that whole main diagonal is gone, right? But the way it normally works would be just to simply say that I am going to form the following function, and I would just simply say consider f that's going to go from z plus to the rationals, and I'm going to say 1 goes to 0, 2 goes to positive 1, 3 goes to negative 1, and then I'm going to start bottom diagonal moving up. So I'm going to go to 1/2 goes, oops, got my head backwards here. 4 goes to 1/2, 5 goes to negative 1/2, 6 goes to 2, 7 goes to negative 2, and then we go back down, so now that we're to 1/3. 8 goes to 1/3, 9 goes to a negative 1/3. We skip 2 over 2 because 2 over 2 plus and minus are not rational, and so we then just say, okay, 10 is going to be mapped to 3, 11 is mapped to negative 3, and if we would look at this ellipsis is telling us what? Continue to follow the diagonals as stated above, right? As I said, we have to state what the diagonals are. If you don't state what the diagonals are, we don't know what do you mean by what diagonals are you talking about. We continue to follow the diagonals as stated and skip any a over b that is not in the rationals. Will this function, if I follow the diagonals like I'm showing, does this ellipsis cover all of the rationals? Are all the rationals in this table? Yes. Will all the rationals get a room? Yes. So not only are really what's kind of interesting about this table is not only are the rationals countable, the infinite versions of every rational number all put together is still countable. That's awfully big infinity, it seems, but it's still the exact same size as 1, 2, 3, 4, 5 to infinity. It's still countable. Kind of one of those things that makes people's heads hurt, right? How many rational numbers are between 0 and 1? An infinite, right? You could just simply keep cutting in half if you wanted to do that. 1/2, 1/4, 8, 16. Any two rational numbers. How many rationals are between any two rational numbers? An infinite number. So what about between 1/5 and 1,000,000th? There's an infinite number. What about 1,000,000th and 1,000,001st? There's an infinite number between those, but they're all still countable. And all the variations of them are all still countable. And you'd like to say, but it has to be, no, it's not bigger. Because why? I can say sit down, and they're full. Nobody's missed. It's one of those things where it's like you would think that infinities like that would be possibly naturally larger, and the answer is they're not. This actually gives us, remember how we had way at the beginning we talked about the roster method for numbers, right? You could just simply list them out in order. Guess what? See this right here? If you would continue that pattern, that would be the roster method for the rationals. Now, I don't know how many people, if I would write 0, 1, -1, half, -1/2, 2, -2, a third, -a third, 3, -3, would catch the pattern. You know, what is that doing? And what the pattern is you write 0 and then 1s, and then from this point on, you write, what are all the rational numbers who top and bottom add to 2? And then I'm going to write all the rationals who top and bottom add to 3. And then I'm going to write all the rationals whose top and bottom add to 4, plus and minus for each. We have to do a plus minus for it. And that's all that roster method does. It's kind of like a subset of approach, right? So the rational numbers, this isn't, if you would look at this particular proof, I wouldn't consider, you know, complete or perfect. When you want to see a proof that's right, you wouldn't want to have it written down. The book has like kind of the beginning. Their proof is not the proof of the rationals. The book only proves for the positive rationals, exclude 0 and negatives. So you have to kind of take what they have, take what this is, and put it together in words, because you have to write it all, that makes sense to you. Or better yet, to the person beside you. All right, so that seems to be that the rationals would probably be quote unquote bigger, but they're not. Okay, what about the reals? All right, the reals are going to be uncountable. And what we're going to do is we're going to definitely use the approach of the opposite way, where for the rationals, I said one technique could have been that this table is bigger than the rationals. The table is countable. The rationals need to be countable. All right, we're going to go the other way. This really big thing is what I want to deal with. But if a small piece of this is uncountable, the entire thing would have to be uncountable. And that's the idea behind the proof. The idea is if I want to prove big thing, and in here is a subset, right? And here is this actual set. So set S is what we want to show uncountable. It's enough to show a subset is uncountable. It's kind of like this whole idea of nesting thing, right? If a bigger set is countable, the smaller set must be countable. But if the smaller set is uncountable, then the bigger set must be uncountable. Does that make sense? Okay, that's the approach that we're going to take for this one. And what we're going to do is we're going to restrict ourselves. So we're going to restrict to all reals from 0 to 1. So that's a subset that we're going to be considering. I want to look at all reals between 0 and 1. So here is 0, here is 1, in here is a real number R. All right. We're going to restrict out to just simply between 0 and 1. Why would we want to do something like this is it's going to take what these reals and narrow them down in terms of what they look like. In a decimal form, as a decimal, R equals 0 point, right? And let's call this, say, real 1. And then what's going to come after this? everything between 0 and 1 is 0 point something. And so what comes after it is a bunch of decimals that are numbers between 0 and 9. And so this would be, say, the decimal 1, decimal 1, 2, decimal 1, 3, decimal 1, 4, etc. Where the Dij is simply some number that's either 0, 1, 2, 3, all the way up to 9. Right? It's a decimal. One of the things that the book does is they say, well, here's a physical example. You can't prove by example, right? Examples are only useful to get it wrapped around your head. Like, for example, is 0.25 a number between 0 and 1? Yes. Is 0.10100100001, is that a number between 0 and 1? Yes. It's 0 point something. I don't care what. It's between 0 and 1. All right? This one is a rational number. The second one is a purely irrational number. Right? It's just a number between 0 and 1. They have decimal forms. All right, we have another approach. In our proof, we are going to what we're going to attack is a particular feature of all numbers need to be here. All right, we're going to use a proof by contradiction. So I'm going to need uniqueness in my proof, which means I need uniqueness in my decimal representations. And so note, we need unique decimals. But what's the problem? The problem is 0.19 repeating is actually equal to 0.2. Right? Remember we did this in the previous class? All infinite number of 9 tailing numbers are actually a terminating decimal in a second form. And so if infinite number of 9 versions are actually a terminating decimal and we need uniqueness, we're going to do the classic thing is we're going to exclude all infinite 9 versions. And so what we do is say we will not allow any infinite 9 decimals. We will just use the terminating form. Everybody okay with that? So far I'm just doing background work. We're saying we're having real numbers. What are you talking about? Decimals, but there's a couple of versions for terminating. We're not going to have the infinite 9 version. So all we've done is say I am going to look at all numbers between 0 and 1, and I'm going to have unique representations by never allowing infinite 9 versions. And so that's what we're looking at. That's our set. We have to have that background to know what we're considering. Now, that set of decimals, so what's our goal? Is to show that this set of decimal reals, right, from 0 to 1 are uncountable. The problem is the word un. Un means what? Not. Big problem in math. Showing things that are not are usually difficult, right? Remember how did we approach the things that are not rational, like the square root of 2? What technique did we use? Contradiction. Why did we use contradiction? Because we assumed it is, right? It's easier to work with objects that are rather than the objects that are not. It's like, what do you have? Not that. Well, I don't like that. I want to have something that I have, right? That's why a lot of times we use contradiction and contraposition, right? Because it negates something. So what I'll do is, for our proof, we're going to use contradiction. So we are going to assume that the reals from 0 to 1 are countable. Now we have something. We have actually something to work with. What does it mean to be countable? there is a bijection. So to be countable means a bijection exists. So what are we doing? We're actually assuming the bijection from Z plus to this set exists. That's what we've actually said. If you tell me that it's countable, you're telling me that this thing works. Well, what does a bijection look like? It looks like this. 1 has been mapped to real 1. 2 has been mapped to real 2. 3 has been mapped to real 3. 4 has been mapped to real 4. And this never stops, right? What does real 1 look like? It looks like 0 point something, decimal 11, decimal 12, decimal 13, etc. What does real 2 look like? 0 point something, I'll call it decimal 21, decimal 22, decimal 23, etc. What's real 3? Decimal 31, decimal 32, decimal 33. And what about this one? Okay, decimal 41, decimal 42, decimal 43, etc. Right? All these reals are a decimal representation. Now, this is a bijection. So what does that tell you about the real numbers on this list? All of them are here, right? It's on to. All of the real numbers are in this list of real 1, real 2, real 3, real 4. All of them are here. So what I'm going to attack is I'm going to ask, wait, all real numbers between 0 and 1 are here? Yes. What about this one? And I'm going to write a real number that I'm going to prove is not in the list, but it's a number between 0 and 1. Does that lead to a contradiction? Here's a number between 0 and 1 that's not in my list, but my list contains all numbers between 0 and 1. That's impossible. A bijection can't exist then. Therefore, they must be uncountable. All right, well, how do I do that? So that's what I'm going to try to attack. I'm going to try to find a real, I'll call it real star, which is 0 point D1, D2, D3, etc. What's nice about like that, try to find real star that is between 0 and 1. Is it? 0 point anything is between 0 and 1. And not in list. But the list contains them all. This is what I'm going to try to do. This is what's going to form my contradiction. This is where uniqueness is important. If I compared two decimal numbers, and I notice that in exactly one position, I don't compare to all of them, but I look at one position in particular, and I notice that the decimals are different. If decimal representations are unique, what would that tell you about the two reals? They're different. Why is that infinite number of 9 being thrown away important? Okay? Note, this is just an obvious thing. If you have unique decimal forms, if one decimal is different, then the reals are different. What I'm saying is, like if I had, say, real, well, let's call it real, let's call it A was equal to 0 point something, something, something for something, 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 dot, dot, dot. I don't really care what those are. But this one's equal to 0 point something, 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 to something, 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 dot, dot, dot. Do I need to compare anything else? If you find one place that it is different, the numbers cannot be the same. That's only true if we have a unique decimal representation. Can you see why this is problematic if we have two versions of the terminatings? Because what do you notice about the terminatings? They're different in an infinite number of places, but they're the same thing. You know, oh, look, they're different in one. Who cares? They could be different in an infinite number and be the same. How do you know that you just didn't accidentally find a second version? Well, what we know is only the terminatings have that problem. So what number should we avoid? 9s and 0s. Those are the things that give us problems. Because I can sit there and say, oh, look, I'm going to make a new number that I'm going to use 9s to make it. No, you shouldn't, because you might accidentally create an infinite number of 9s, and the thing that you said is not there is actually there in its terminating form. All right, so how am I going to do this? What I'm going to do is do what's called Cantor's diagonalization. Is he goes down this main diagonal, and he says, all right, I'm going to make a new number based upon your list. So this is your list. I don't care what you wrote. What I'm going to do is we are going to make r star equal to 0.d1, d2, d3 in the following way. If d11 equals, and now here's my technique. My technique is the following. I look up here. I'm going to make my first decimal not d11, and not 0 and not 9, because 0 and 9 are bad, right? So I need to pick something that's not d11, not 0, and not 9. How can you do that? Well, one way to do that is to literally say, pick d1 to be not d11 and not 0 and not 9. You could actually just say that, right? We could go through here and say, instead of saying this if thing, we are going to do this. We're going to let d1 be not d11, not 0, not 9. These are important for that whole terminating infinite number of 9 problem that we're trying to avoid. But if it's not d11, that immediately tells me that r star cannot be r1. Does that make sense? They're wrong in one spot. Okay, then I'm going to move on to the next one. I'm going to let my second decimal be not d22 in the not 0, not 9. Why? Because, again, that's the terminating. But that tells me that r star cannot be r2. Continue. R star cannot be Ri for all I. Does that make sense? What do? I just keep going down and say, not that, not that, not that, not that, not that. And then it's like, I have made a new number between 0 and 1 that is not in my list. So is that a contradiction? Yes, because my list included everybody, except this. That's not allowed. You can't say I have everyone but you. That's a liar, right? If I said all the students are in the room right now, and then there's somebody standing in the hallway, it's like you'd look, no, right? And so normally we put the for all I first. Let's put it in the right order. For all I would normally go there. So for all I, r star is not Ri, and that's my contradiction.
Does the uncountable set give its own symbol, or the like null?
Yes, it's a weird, for the cardinality of the reals, the cardinality of the real numbers is this weird, I think it looks like a C. It's like a script C of some sort. Kind of a script C. Script lowercase c. On the other hand, there's a question that's open right now, that's been open for a very long time. It's called the Continuum Hypothesis. And the Continuum Hypothesis is the following. One thing we can notice is if I look at the reals, I guess I can talk a little bit, just a quick definition of it. Any decimal number, right, would be just simply a collection, if you look at the numbers themselves that we pulled out, right, it would be I picked some sequences of ints, right, where there's some to the left and some to the right, if I look at that. And so you could sit there and say that, you know what, the real numbers in their decimal form are essentially a power set representation, one of the subsets of selecting some of the ints themselves. So it ends up being that you can show is that the cardinality of the power set of the counting numbers is actually the same as the cardinality of the reals. The Continuum Hypothesis says that could we build this, which ends up being that has to be 2 to the cardinality of Aleph null. So 2 to the power of Aleph null is the cardinality of the real numbers. And the Continuum Hypothesis would say that if we would define this as a sequence, say Aleph 1, do the infinities break up into this concept of a countable collections of the infinities. So the infinities are, you have the ones that are like the integers, and then the next ones are 2 to the power of that. All subsets of them would be all the guys that are like the reals. And then we would take what's all possible subsets of the reals. That would be the next group, whatever it looks like. And so it would find this grouping that goes up. This is an open problem. So.
Then maybe with A left to the in the reals?
No, this is the reals.
Oh, okay, so,
There's other ones that are even bigger.
they're bigger than reals. Okay.
Yes. What should we take the real numbers and what's the power set of the reals? So, anyways, that's it. Sorry I went over, but we lost 10 minutes on this. Or 15.